for that introduction. I'll share my screen now. That should be up. Okay, so thanks for joining. We're very excited to be a part of this. I personally am excited. I'm able to shift away today from our traditional technical webinars where we dive into some of the more analytical aspects of designing and specifying fiber optic links and some of the intricacies of the technology. But today we're in a knowledge sharing mode. And I'm excited to share the lessons learned and some of the experiences that I have found over the years to help you as a potential user of this technology to make decisions and avoid some of the common pitfalls. Very brief introduction before I get started. For those of you that are new to Microwave Photonic Systems, we are a systems engineering firm, and we have core technology in RF over fiber transport, but we have providing custom solutions, integrated systems to a broad base of users and market segments. Been in business since 1999. So the goal of the Tech Tuesday is, as I said, to knowledge share and communicate lessons learned and common pitfalls. And ultimately, I want to convey to you, as somebody who may be considering using fiber optic technology, that it's mature and it's robust, that it's a scalable solution, and that successful deployments really require a systems engineering approach. And by following some of these steps and by avoiding some of these pitfalls, that you can make decisions that really support value-based decisions that add and enhance capability to your transport architecture, and that will meet not only your current demands, but also set yourself up for future iterations. And ultimately, after hearing some of the key points and learning about technology, that moving forward, you would consider contacting our team to be considered as a teaming and solution provider for your future requirements. So first and foremost, if you're considering adopting the technology, that may mean that you're new to the RF over fiber domain, and you may need some information to establish that it's ready to fit the bill. And you can see that the optical technology is not necessarily new. As a matter of fact, the real first RF over fiber links started in the early 90s, and by 1992 it was deployed on Navy ships to support GPS navigation systems. And you'll see over the years that what has happened is the capability has increased, the bandwidth has increased, the dynamic range has increased, and now where we're really pushing the envelope is it's a key consideration for applications well up to 60 gigahertz and well over distances of fiber beyond 100 kilometers. And now the question would be, okay, well that's great that it's mature and it's robust, but why use fiber? Well, the answer is quite simple. First and foremost, the data carrying capacity is much greater than that of copper. And when you're designing a traditional coax-based system, one of the things that I've always struggled with, and it's going to be around as long as people are using coaxial cables and waveguides, is managing loss over frequency, and fiber offers a very unique characteristic that there is uniform loss over frequency. So you won't see the contribution of slope from the RF photonic transport over many kilometers that you would if you were to have traditional coaxial waveguides. The other main reason to use fiber is that it does offer a immunity to lightning strikes and RF interference and an added layer of security. And while there's some other bullets listed there, those really are the main reasons. One, you can go much further distance with fiber. Fiber offers about 0.2 dB loss per kilometer. It's uniform in that loss over broad frequency ranges, and you get an added ability to isolate either sensitive radio equipment or secure equipment in a SCIF boundary layer from that of the exposed antenna apertures. So first and foremost, when I reference a fiber optic link, a fiber optic link consists of three main components: a fiber optic transmitter, a fiber optic receiver, and an interconnected cable. And for analog RF photonics, there's really one key methodology. Now, there's many others, and we discussed some of these in our other webinar series, but the most commonly deployed that's out there is what they refer to as IMDD, or intensity modulated direct detection. That is, the laser is modulated, uh, varied in optical signal intensity, thereby imposing the analog signal on the optical carrier. And the process of doing this presents a format agnostic neutral host transport methodology, which doesn't put encryption. There's not an analog to digital converter. We're not signal processing this. So you get very high fidelity signals without any additive processes imparted onto that signal. So it can be independent of data modulation and formats. Now, there are two different types of fiber optic transmitters. You'll hear the term externally modulated and directly modulated. A directly modulated fiber optic transmitter has an integrated semiconductor laser, which handles both functions of not only providing the discrete laser source, but also the modulation source. An external modulated system would use a dedicated laser as the source laser, and then a separate component to modulate that. The trade-off in that is if you're working with signals below 20 gigahertz, you're typically limited in performance to sticking with a directly modulated system. When you start to go out beyond 20 gigahertz, you are now considering an externally modulated system, which does increase size, weight, and power consumption. Further to that point, when thinking of RF over fiber applications, it's not the same as what many people are familiar with, where they might have an Ethernet over fiber transceiver or a serial to fiber converter, where what the fiber optic transmitter is doing, it is looking for that state change or a level shift and is transmitting that signal by way of turning the fiber optic source, whether it be an LED or a laser source or a vertical cavity type source, to having the light turned on or off. That's not what we're doing here. As I said on the earlier slide, the RF input is direct detected. We sample that. We then modulate the intensity of the laser, and the fiber optic receiver does a direct detection on that and then transposes that onto the RF carrier. So again, it's a format agnostic. It is not processing any of that. The signal that you provide at the input is then reflected at the output of the receiver. There's many design considerations. Some of the basic aspects of a fiber laser go into the frequency response, the conversion efficiency, whether there's an integrated thermoelectric cooler, and these are all different design considerations. And today, just as it was many years ago, the major contribution to noise in a fiber optic link is the laser. And that is why making sure, as we'll speak later, defining the requirements of the system and doing proper systems engineering and requirements decomposition help to design in the best approach for the fiber optic transmitter. Similarly, with the fiber optic receiver, there's many different types of detectors that can be considered. And again, these have a conversion efficiency, they have a certain responsivity, and in managing the fiber optic link budgets and the fiber optic performance specifications, these are some of the detailed design considerations that must be given. The reason I share all that with you today is because that's one of the common pitfalls. There's been 30 years of maturation in the fiber optic marketplace. Everything from the cell phone and the 5G booms have really driven market demand for better performance within the integrated circuits, better performance within the available packaged amplifiers and semiconductor components, fiber optic components, lasers. All of that has now yielded the ability to produce very mature, very compact and scalable solutions that are equally ready to be deployed into the commercial marketplace or the military defense marketplace. And that's, as somebody who works in the systems engineering and interfaces with the clients, that's probably one of the first things that I have as a deployment hurdle is working with clients, explaining across the organization that maybe there's somebody with an organization that says, oh, well, I tried using fiber 20 years ago and it was very noisy. Or I tried using fiber 10 years ago and boy, were they big. And I would urge you not to fall into that pitfall, that there is in fact a very, very broad base of technologies out there that now support small form factor, highly reliable solutions that have been commercially and military certified to a full slew of safety, electronic emissions, as well as shock and vibration qualifications. So next, let's get the creative thought processes going and discuss some high-level applications. The markets listed here are the most common market segments where we're deploying fiber optic technologies. And within each one of these different market segments, there's different types of requirements. But the recent modernization of photonic-based technologies has absolutely generated application-specific hardware, which can now be deployed in large-scale systems such as, say, a SATCOM Earth terminal and teleports, to very small form factor airborne and UAV applications. This is a very common type of an application, a SATCOM fiber optic interfacility link. You'll see on the left slide here, there'd be a fixed operation groups, maybe the central hub that's doing the data processing, where the remotely located antenna group is connected by an interfacility link cable. Traditionally, this could be coaxial cables. Using fiber optic technology, you can deploy a high density integrated rack chassis that provides a number of different features listed here on the right to support various mission scenarios. Delay lines and network simulators are also a big portion of fiber optic technology. I've shown here a functional block diagram and a representative unit for scale. And you'll see that there's fixed delays, there's switchable delays, there's delay lines which can be programmed. And well, where would you use this? Well, if you wanted to simulate network latency, if you wanted to simulate a target, or if you wanted to create a piece of equipment that would calibrate radar altimeters or test certify a radar system, you would want to use something such as the delay line. Here in this functional block diagram, you'll see that we position a amplifier in front of a fiber optic transmitter. For this specific scenario, the rationale for that was to provide a certain gain, noise figure, input third order characteristic. And we have the ability to, once we convert that RF signal to the optical domain, to put that through a series of optical switches to impart the desired delay. The benefit of fiber optics is twofold. One, as I mentioned earlier, you have the ability to impart a uniform loss over frequency through the fiber optic, but also the ability to create delays in very compact small form factor optical delay spools. It could not be achieved effectively by doing that using large coils of fiber cable, especially considering that these delay lines can operate well up to 18, 20, 40 gigahertz. Precision navigation is also another market segment. You'll see here in the left some representative performance. The top left would be a modulated iRig signal. You'll see the two different traces are showing that the signal is being maintained There's no corruption in the fidelity of that signal. However, it is time shifted a little bit, and that's accounting for many kilometers of fiber. Actually, if you look at the data here, you'll see it's about 3 microseconds delayed. But you'll see even through that 3 microseconds is a significant amount of fiber cable. The benefit of that is now we've just remoted a time signal, and we have not impacted any of the amplitudes or the frequency of that signal. The applications could include GPS, iRig, both modulated and unmodulated, 1 PPS, and also 1, 5, 10, whatever your frequency reference may be. Tow decoys, tethered drones. Here, one of the key considerations is size, weight, and power. Stripping down some of the inherent capabilities in order to provide a form factor that supports a power budget, that provides the capability to do optical multiplexing to minimize tether weight or the towed interconnection weights, to provide optical level control in the sense that depending if this is going through a rotary joint or some sort of slip ring, there may be variations in that optical level, and we'll want to be able to maintain that so you don't see any of that present itself as signal bursting when we convert that back to the RF domain. Further, there's considerations for hybrid copper and fiber optic cable assemblies. Here you'll see a pictorial which demonstrates a piece of a cable which not only would have a fiber optic cable, an integrated retention device, but also copper for powering the remote equipment. Broadband signal detection is another common application. Here, key considerations in specifying a fiber transport solution for that would be dynamic range, the phase noise, thermal stability over time. How do you do the channel segmentation if you're doing multiple lobes or looking at different beams? And if it's extremely remotely located, how would you provide remote powering to equipment that may be tower mounted or operating in some sort of remote location? Distributed antenna systems, very common application for in-building public safety or trunked radio repeaters, common for providing communications coverage within tunnels or underground metro systems, common across business campuses or academic campuses, and becoming increasingly more common in the commercial and military segment for in-hangar re-radiation to be able to validate communications protocols, validate navigation alignments either during manufacturing or perhaps post maintenance activity. Another big area is range simulation and EMC testing. Here you'll see a functional block diagram for a specific application where a user was interested in having multiple probes within a chamber environment, and often was operating different scenarios in different chambers, but had one central processing. And the goal was to be able to maximize the antenna elements and the probe elements, bring that information back to the processing center and be able to be rapidly configured to analyze the signals. The benefit of the optical cable in this was, well, in an EMC environment, you don't want to have the coaxial cables running through the chamber. The shorter you keep those, the more that you can minimize the potential introduction of outside signals, the better that your ambient environment will present itself. And then another example would be tactical radio remoting, where you want to remove the troops or the staff or personnel from the transmitting equipment to be able to essentially remote the front end of the power amplifier and the radio to isolate yourself from a potentially targeted threat. So that being said, without going into each one of those, as I've mentioned earlier, we're more than glad to host a webinar specific to some of those topics. But all that being said, one of the common pitfalls is forcing the technology, that there are instances where sometimes the technology doesn't pass the down selection criteria. And although it's a novel approach to remoting information, remoting data, sometimes, well, it's not necessitated, or in cases where it does pass a down selection criteria as a technology to be inserted to solve a specific solution, that adding complexity and additional components may not be necessitated. I've seen many applications, sometimes in airborne applications, where by the time you go through the trade study, although the fiber optics does simplify the cable harness integration, it does simplify some opportunities for EMI injection onto the coaxial and copper cables, that by the time you add in the fiber optic equipment to do that conversion and transport, you've now consumed weight budget, you've consumed power budgets, and you're adding thermal complexity to that environment. So as much as I want to be a supporter and somebody to encourage using the technology, surely trying to force the technology to a scenario where it's not applicable doesn't help to establish comfort and positive experience on the user. So I encourage you to consider all those additional deployment concepts and to do your trade study to evaluate whether or not it meets the minimum set of requirements. So if you've gained the confidence in using the equipment, if you found applications where you believe that it can be used and you think it'll map into your communication strategy, it's equally important to define what you need. And next, I'll discuss some systems engineering best practices on how to specify a link. So as I've mentioned before, the fiber optic devices really are systems of systems. There's a core technology which falls into the laser, the detector, and the supporting electronics. And that equipment moves up a technology hierarchy, which can then become a module, a subsystem, or integrated subsystem. And by having design control over the core technology, we're able to support multiple tiers of integration from the module level to the subsystem level. And in doing that, I always encourage potential customers and clients to do the requirements analysis and decomposition. That while in many cases I consider these commercial off-the-shelf systems, some of it is slightly modified or really engineered to order, whether you're a new user or you've been using fiber optics for a long time, is don't fall into the pitfall, don't ignore the systems engineering process. And the more that you can do to follow a strong systems engineering process to decompose, it allows us to not only mitigate overspecification of the fiber optic link, but it also helps to reduce costs and manage schedule expectations. One of the things that you can do is you can engage with us or engage with other members of your team to try to conduct a link budget analysis. Now, what we do here is we have the same process. We can help to write a performance boundary around the fiber optic link until where we can define each aspect of that system in terms of noise figure, traditional linearity characteristics, harmonics, and allocate that performance across the transmitter. Similarly, we can allocate that across the fiber interconnection plan, across the receiver, and wind up with a full cascaded analysis of the RF fiber optic link. Now, this is another common pitfall that I see some of the clients falling into, is what I'll call overburdening the fiber link or the optical transport system for ease of modeling. And what I mean by that is either setting a unrealistic requirement for noise figure or simply defining the link as unity gain. Now, we sell many links and I've seen many solutions where it is unity gain, but if you're versed in traditional RF and microwave engineering, you've got to get it from somewhere. So what I suggest is when you map your system, if you're transitioning now from, you want to go to let's say a 20-kilometer system, well, I challenge you to find a 20-kilometer piece of coax that's unity gain. That most systems already have some sort of tolerance or expected loss characteristics or acceptable noise contribution from the cascaded elements. And by doing the upfront systems engineering to be able to decompose those requirements and clearly define the fiber optic link as an envelope allows us to now get into the trade study to provide an optimal system that not only provides performance, specification compliance, but also falls in line with the best value case, best business case for deploying that fiber optic link. Here's where I'll spend most of the time today sharing some of the common pitfalls. And the reason for this is that the most common troubleshooting call that we receive, the most common problems that we have deploying engineers into the field to validate systems always comes back to the fact that the structured cable plan and the interconnection plan is not prioritized. This problem has no preference to projects large or small, and it's common across all market segments and industries. For those of you that aren't familiar with optical fiber cable, the construction is quite basic. There is a central core which the optical signal travels through. There is cladding around that core which helps to maintain the continuity of that light traveling through the core to maintain the characteristics of that, and then there's a coating around that as well. And there's many different vendors with many different variations, so there's all kinds of different trade-offs that you can make to satisfy your interconnection plan. It's very easy to identify these cables. We, RF photonics, analog photonics, use single mode optical fiber cable, and there are different types of cables. So this is just a side, it's a quick reference chart. The reason I put it in here is I do get a very common troubleshooting call where they're trying to hook up multi-mode optical fiber cables to a single mode optical fiber system. There's many different connectors for applications. There's angled connectors, there's multi-termini connectors, there's ones that are more of a snap-on RJ45 style, where there's others that have more of a bayonet fitting. And again, this is a consideration that you would want to think about in terms of what's the deployment environment, what's the density environment, does it look like there's going to be subject to a lot of shock and vibration? You may want to consider different termini or different connectors. There are multiple types of optical connectors as well, but they're all common in essentially 3 different types of polishes, or I should say connector types: the PC, the UPC, and the APC. In RF analog photonics, you'll typically find that the angled physical contact connector, sometimes intermittently changed as said angled polish connector, is used. The reason for that is that angled polish, that angled physical contact, minimizes back reflections and allows for better stability within the transmission source. Connectors in themselves go together very similar to any of you who have ever made or handled a traditional coax connector. You strip the fiber cable, you expose the center conductor, you insert the fiber into the connector, there's a crimping process, the epoxy cures within the connector, we then polish that connector and it gets tested. The reason I'm sharing that is because this is leading up to one of our next major pitfalls. As I said, a lot of times the optical connectors are either deprioritized, or they're put off to the last minute to buyer, just saying, oh, all connectors are the same. Well, that's not necessarily true. The polishing process, the process by which the manufacturing of an optical cable is finishing that assembled connector, removing the excess fiber and polishing it down into its appropriate shape, really takes years of experience. It requires strong adherence to protocols, work instructions, and processes to make sure that there's a repeated end face geometry each and every time, and also defect free. And there is standards that define this. But one of the most important things is the ability to certify it. There's a certification testing which can be done using interferometry, which looks at the end face of the connector. The end face of the connector can tell you two different things. One, it can tell you where the physical apex of the connector is to where the geometric center of that connector is. And that's what we refer to as fiber offset. You can also look at the curvature of that, and that's what we refer to as the apex. So you'll see a perfect apex due to interferometry, those rings, think of it as a topographic map. But the closer and more concentric those circles are aligned to the center indicates the apex of that connector. And that's a common pitfall. If you go online and you look across the market segment to buy a fiber optic cable, you might find one at $15, you could find others at $30, you could find others at $75. And that directly correlates to the quality of the connector. So assuming that all quality is the same, and when procuring cables or having a secondary contract, perhaps do the installation work at a site, make sure to require certification reports. I've seen that happen a lot where a statement of work will be written for everything and all the details are in there and all the acceptance criteria is written, and then you look at what was expected for the fiber cables and there's no language written in there relative to the quality and the certification reports of the cables. We have other webinars that I've mentioned which discuss specifically on end face geometry and optical cleaning and inspection criteria. And if you'd like that, you can send a text through the chat or let us know and we can set that up or share that webinar with you. But here is where you can really see a good apex versus a apex offset. This is a moisture ring, which happens when you obviously you insert solution into a cleaning connector and you don't get rid of it. But what you'll see is a big offset between these two connectors. And if you refer to some of the earlier slides where I showed the different types of fiber cable, for single mode fiber, we're talking about a 9-micron center core of fiber. That's extremely small. So if you get this offset alignment between two mating connectors, well, that's going to cause a reduction in power loss. That's going to cause increased back reflection, and that ultimately is going to present itself into a transport solution, consuming loss budget, and in RF it'd be essentially loss and link gain. Further the process, it's really easy to get these connectors dirty. Either they can be contaminated with dusts, hand oils, improper cleaning devices, they can be scratched. And again, if you look at that top left connector, you'll see how small that core is in the cladding. Very important to keep these connectors clean. For illustrative purposes, this slide shows the 9 micron with the 125 micron Next common pitfall: assuming new cables are clean and not adhering to best practices for connector handling and cleanliness. A lot of people refer to the caps on the end of fiber optic connectors as dust caps, and that couldn't be further from the truth. They're protective caps. Don't ever assume that just because you've taken a new connector out of the bag from a manufacturer, even with certified test report, that it's clean. A lot of these protective caps are made out of a plastic. They tend to attract dust, and they absolutely need to be cleaned before connected to the equipment. One of the terminology we hear when discussing fiber optic systems is a structured cable plant, and that refers to the total solution, the total interconnection plan, what support hardware is being used, how are you getting the signal from the transmit location to the receive location, how are you routing it across the rises within the building, is it going to a telco, patch panels, or IDF locations? And when considering the structured cable plant, there's a lot of considerations. There's outdoor cabling, and you'll see here I've tried to put these considerations in there. What's the breakout cable strength? Does it need to be a high tensile strength cable? Should it be an armored versus unarmored? Is it going to be lashed, or does it need to be self-supporting? What type of UV protections you need? If you have a cable perhaps that's going to be in the desert or versus going to be in an Arctic region, those are two very different fiber cables, and the market base has many selections to be able to support that. Rodent protection. Many a times I've seen in the cable television business, the squirrels sure do like to chew through the cable. Direct burial cable. This is something that comes up quite often in the radio astronomy or antenna array application, where there's many different antennas spread across a range. And one of the things you want to do to maintain phase stability is to get that fiber cable trenched down below the frost line to keep it as steady as possible and align that. And then there's a whole different considerations for that cable. Is it water resistant? Do you need pulling eyes? Is it going to be trenched? Or are you going to pull it through a duct or a conduit? How do you maintain bend radiuses? These are all very important considerations. But ultimately, if I were to have to point to one common pitfall in all of these, is the inside plant, the indoor-outdoor running of the cable, and where it really costs time and money and resources. And that is the pitfall of not pulling extra fiber in order to avoid the perceived extra costs. If I were to show you a pictorial of the diameter of a fiber cable that had 1 fiber versus 12 fibers, it's almost the same. It's what I call the garage or the garden shed effect. The minute you pull that cable, or the minute you build that garage, you realize, well, it's already too small. I've already used up the capacity. The money, the deployment costs of pulling the fiber and routing the fiber and putting in the structured cabling, patch panels, the junction boxes, getting the clearances to run that through. By the time you lump in all of those costs and the labor elements to add additional fiber strands for either spares or upgrades or future expansion, really is in the noise of the total systems acquisition cost. And that's not to be said that I don't appreciate budgets and budget constraints. I'm simply pointing out the fact that when planning for long-term use or long-term deployments and consider future-proofing deployments, that this truly is one of those instances where paying the money up front really does avoid downstream headaches. So summarizing the optical cabling plan, you'll see some of the considerations for interconnection selection, cable selection, as well as channel management. Here's a summary of different type of questions that I would suggest asking when considering a fiber optic system and paying due diligence to the optical structured cable plants. So the common pitfall here again is treating the optical interconnects as commodities akin to RF cable assemblies, which are prioritized later in the program. I really urge anyone considering this to put that up front. They get the fiber optic cable as much of a critical component in a transport system as the physical transmitters and receivers themselves. You can't look at the fiber cable like a traditional coax connector. You need to look at it that it's a waveguide. And just as you'd spend time to specify a waveguide, you should spend that time up front to define the minimum set of requirements for the fiber cabling, to consider the field serviceability aspects of that cable, to think about the distribution aspect of that, to look into local regulations. If you're on a shipboard, you're going to need a shipboard rated cable. If you're going into a plenum within a building, you're going to need a plenum or perhaps a riser rated cable. So there's a lot of design considerations related to the fiber optic cable, and they definitely should be prioritized upfront and early. One other thing that I've learned through these deployments, that another common pitfall is cutting costs by not procuring the proper test and certification equipment and looking at that as a sustainment cost or a reliability, maintainability, supportability, logistics cost, and waiting until there's a problem. And that really is a difficult situation from our standpoint, from a manufacturer standpoint and support engineering standpoint, is because it's like not having a voltmeter or not having a network analyzer or something to be able to validate the RF aspect of the system, and to not spend that equal investment to have some basic troubleshooting devices such as an optical power meter or a visible fault finder or a light source to go out there and troubleshoot your systems and be able to isolate perhaps something got cross-connected on hookup in the field. Maybe there's a bad fiber that was spliced poorly by the integration team or the subcontractor who pulled the fiber. So pushing that equipment to later in the program doesn't bode well for being able to address and identify issues early on. And surely procuring the equipment when there's a problem doesn't give the technicians or the team members out there trying to troubleshoot the issue enough time to really learn about the equipment. Next, I encourage you to think systems oriented. When architecting a system, if you were to map down the functional block diagram of what you're trying to achieve, one of the starting points that I always urge is draw it just like you would if you're doing an RF system, because in the photonic world, there's devices that mimic the RF world. So there's fiber amplifiers, there's optical switches, there's different types of optical switches, just like RF switches. There's latching, there's fail-safe, there's asymmetric matrices, there's optical attenuators that can be fixed value or variable. Those can also be manually controlled or electronically controlled. You can do multiplexers and demultiplexers in optical by assigning different optical wavelength channels. There's splitters and couplers and power taps. There's circulators and filters. So there's a whole bunch of different devices outside of the core RF to fiber and fiber to RF conversion equipment that allows for very complex and intricate subsystem solutions. And when you couple that along with the other support in RF microwave expertise, you can come up with some very elegant integrated subsystems that not only alleviate the ultimate integration aspect to you as a potential user, but also provides for sharing of capabilities, further embedded processes, and optimizing the solution set to leverage the expertise of the RF, the microwaves, and the fiber optics into one integrated system. Many times I comment that although we call it a fiber optic system, the smallest portion of the system is the fiber optics. That a lot of the other equipment is the signal conditioning, the switching capabilities, the bias injections, the monitoring software. And don't limit yourself to just thinking about deploying RF over fiber as a point-to-point solution or a modular level solution. That, as I've illustrated earlier, these are very mature, robust technologies that can in fact be integrated into complex systems of systems. So in summary, what are the common pitfalls to avoid? First, don't ignore the 30 years of the continual maturation evolution. Conduct a market survey of your own, look across the market segment. Surely I would encourage you to engage our team here. Don't feel need to force the technology. That adding complexity, as I said, may not be needed. Multiplexing may not be the right strategy just because you can take multiple optical channels and multiplex them down onto a single fiber. There are compelling reasons for cost and complexity to say, well, you're better to use discrete fibers for each one of those. Don't bypass the systems engineering review process. The systems engineering review process helps make value-based decisions. It makes it much easier for us to engage with you, or for you to engage with any of the potential suppliers in the market segments on what you want, and allows for consultative engineering type processes to occur. Don't overburden the fiber link for ease of modeling. Treat the fiber link like any other active component. So if you draw a boundary layer around the input and the output of the system, and you can allocate the correlated RF performance parameters, that makes it not only easier, but it makes it much more streamlined for a company like us to respond and present a subset capability and convey to you as a potential user the trade space within that capability. Don't forget the fiber requirements. Make sure that you embed those within your system spec requirements, that you're flowing out requirements to your vendor base, that you're not buying fiber cables based on lowest cost. That's really, that's like buying a Ferrari and putting the used low-cost tires on it. You surely are not going to get the performance, and you're surely not going to meet your specification requirements, and you're not going to have anything to really hold that supplier's feet to the fire if you're not requiring test data, that you're not holding them to the Telecordia standards, and that you're not requesting the appropriate certification reports, just like you would if you were buying frequency reference or phase matched cables, or any type of coax cable. You would expect that, and surely you want to do that for the fiber cable. Don't skimp on the cleaning. Invest in the tools and the training. We offer some webinars on the handling, inspection, and testing of fiber optic interconnects and cables. If you're interested in that, again, you can let myself or any one of the team members at Vic Myers know. We'd be more than glad to do a webinar on that. Don't trivialize the structured cable plan. Prioritize that like any other subsystem element. Don't kick it to the intern. That's as much, again, as a important element of the communications backbone as a waveguide would be. And don't underestimate the future demand for fiber or systems requirements creep. If you've been doing it long enough, you know there's always systems creep, there's always new requirements, and having that systems engineering process surely helps to define the future and current requirements. So with that, I'll end it. It looks like I'm just over my 45-minute allocated time, and I appreciate you listening. And I'd like to open up the floor for any questions and answers.
Thank you so much, Josh. Yeah, we're open up for Q&A, so feel free to send those into the questions box. And I'll just remind you, I have uploaded the handouts from today, the presentation that Josh gave, as well as the product line cards for Vic Myers Associates. So again, feel free to send in any questions you may have, and we have the time to go through a few of them. So don't be shy, send them over and we'll take a look. I do have one here. The first one that's come in says, Josh, what are the critical design parameters I should consider when evaluating a fiber optic link?
Sure. Going back to what I had said earlier, one of the critical design parameters is treat the fiber optic link at first, on your first order pass on trying to fit in a fiber optic system. I wouldn't get caught up into, well, what are the performance specifications of the transmitter? What's the performance specifications of the fiber? And what are the performance specifications of the receiver? To treat the system just like you were to be specifying any active component like an amplifier. You have a frequency response, you have a desired noise figure, gain, input compression, and if you can distill that down by doing a requirements decomposition, that allows us as a systems engineering team to now match our product portfolio to the appropriate passband. So if to just simply say, oh, I need a fiber optic link to go 10 kilometers and I like it to be 0 dB gain, that just, there's too many options for us to propose to you. So again, just like an amplifier, well, I need a 2 to 18 gig link. I have 3 uplink channels, 4 downlink channels. I like 10 megahertz. The more information up front that specifically can be defined to correlate RF performance parameters, coupled with the environmental concerns and with the deployment concept, allows us to very quickly point you in the right direction, give you the appropriate mix of products that meet that subset of requirements within your given application.
Okay, great. Thank you very much. One here that says, how do I model a fiber optic link within my system?
Sure. If you've done RF link budget analysis, this is a good question. It really echoes to the question that was just asked. Again, you can define the fiber optic link just like any other nonlinear device. And what we like to do here is, if you provide a subset capabilities, we can do two things. One, we can very quickly give you actual parametric data from a representative model, either in a S2P file, so you can plug that into your link budget analysis, or we can just give you the raw point data, and you can fit that into a cascaded spreadsheet or predictive modeling tool, just like we showed earlier. So that's one of the ways that I like to engage the client base. As an engineer myself, I always like real data. So if you're thinking about deploying it and you've got a good idea of what you think you might want, define it for us in terms of the traditional S parameters and nonlinearity characteristics, and we can surely specify a comparable link and provide that data for you to help with your modeling.
Awesome. Can you elaborate more on the achievable noise figures and how it relates to design trade-offs?
Sure. Very early in the presentation, I talked about one of the pitfalls is to not to discount or not to ignore the particularly the last 10 to 15 years of developments in either MMIC design, even just at the foundry layer for some of the laser sources that are much better controlled in terms of line width and temperature compensation. What's happened now is we can achieve very low noise figure links. And the difference is whereas maybe 20 years ago, you would see a big preamplifier, or you'd see a discrete post amplifier on there. By doing very tightly coupled design, looking at proper coplanar waveguide designs, all of that control circuitry, all of that's RF preamp in front of the laser to overcome the dominant noise source of the laser, and the signal conditioning once we come back into the RF domain on the receiver allows us to achieve noise figures as low as 3, 4, 5 dB. And of course, what comes with that is a correlation to a lower input compression. So it's always a trade, and that's why I go back to don't arbitrarily, for ease of modeling, assign, oh, well, I'd like to have a low noise figure 0 dB link gain. It works nicely because it just slides into a link budget analysis, but it does take away from somewhere. So we can achieve spur free dynamic ranges, in excess of, good high performance link, 112, 114, 115 spur free dynamic range. Equally, we can use other techniques when you move into external modulation, use different pre-distortion characteristics, we can achieve even greater. So don't shy away from the technology because some of the legacy mindset has been, well, they're large, they've got high noise figures, they've got poor dynamic range. No, these systems absolutely are used in current modern day frontline EW applications, signal intelligence applications, signal collection exploitation applications, EMC chambers, and you absolutely can use these in systems that may require high input power handling or have need very high sensitivity and low signal detection capabilities.
Awesome. Yeah, thank you very much. Here's one, and I'll just say as we're getting close to the top of the hour, if there's any more questions, we've got one more here. We'll maybe have time for a couple more. But again, feel free to reach out to MPS or VMA at any point in time if we can help you out with any of your requirements. One here says, how do you handle extremely long haul fiber requirements?
Right. So I'm seeing a transition in the market segment right now, uh, is trying to leverage existing fiber network, because 20 years ago there wasn't as much fiber built out either in metro areas or going out even to rural areas. And you see in the marketplace, well, fiber optics is everywhere, right? 5G is rolling out a lot of fiber. So now certain operators are starting to consider two things. One, how do we leverage the existing fiber that's out there to go greater distances if we're doing some sort of city to city distribution, or perhaps at a test range where they want to, due to cost savings, want to kind of consolidate and centralize test assets, and just really spend the money in increasing the fiber plants with a campus deployment of fiber. And when you get into that, you start seeing, well, there could be 20 kilometers of fiber between point A and point B, 50 kilometers, 75 kilometers. And what occurs as you start getting into these greater lengths of fibers, one, you have more loss, so you need to start considering the use of fiber amplifiers. And secondly, you start to see the impacts of dispersion within that fiber. And there's techniques where you can do dispersion compensation, namely chromatic dispersion. You can also buy certain fiber cable, which is dispersion shifted. And in the balance of dispersion compensators and fiber amplifiers, you're now able to deploy these optical systems well beyond 50, 75, 100 kilometers and still achieve very high spur-free dynamic range systems.
Wow, definitely some progress on that. So that's good information. I think we're going to wrap it up here, and just want to remind everybody we will send out an email with the PowerPoint as a PDF tomorrow, along with a video link. So if you want, you can share it with your colleagues. And we're certainly available for online or in-person applications engineering discussions, depending on the situation. So feel free to reach out to us at Vic Myers Associates or MPS directly. We'll make sure all of our contact information is included in the email. And we really appreciate you taking the time to hang out with us and learn a little bit more about what I think was a great list of pitfalls. Josh, you did a great job really outlining that. Thank you so much for your time. And thanks everyone for joining today.
Great, thank you for having me.
You bet. Take care.